All right, welcome to the next lecture, and boy do I have a show for you today. So, we're going to be talking about objects and classes, and this is, if you remember that example, you were brave enough to watch it at the beginning of the class, you're going to understand everything about it now. Okay, that counter example, if you remember it back in the day. So, are you ready? This is a very, very exciting lecture. So the first thing that I want to talk about is structs, and this is short for data structures, okay? Data, that's really hard to read, sorry, let's fix that. This is short for data, oh, there we go. Data structures. And so, hopefully with that term you can kind of understand what it's attempting to talk about. A data structure is just putting a bunch of data together in a nice structured way. Okay, so are you ready? I'm excited. We are going to make our own types now. Okay, a struct is a way to make our own data types. We can put what kind of types we like inside, and we can give them all names too. Okay, it's really, really exciting. So I'm going to show you an example on the next slide, don't worry. The idea is you can make a box. You can make a box that holds boxes. Then those boxes have names. Okay, this first thing has a name, like this is S for your struct, right? And then it has X, Y, Z, and P inside of it. Whatever types that you want for these. They can have whatever name you want, whatever types you want, and they all stay together. It's beautiful. It's one big happy family. Okay, so those are structs. You can put whatever types you want inside, and you can name them. You can name what's inside, and those things inside are called member variables, okay? Those are the things that are inside that have names. So a struct is a data structure. It's a way of organizing a bunch of different kinds of data. Sometimes you keep all the same stuff, but different kinds is okay too. And I think I wanted to say the word every. Every element inside the data structure has a name. And yeah, everything that you store inside a struct is just one big package that you can move around all together. Like it all stays together. That's the beauty of it. They all happen at once. So yeah, that is the point. It's very similar to a vector in that you can have a bunch of things of one type, but now you have names for the inner stuff, and you can have multiple types. And now let's talk about it. So my easiest example for you is a point struct. So we're going to make a data structure that keeps track of x, y coordinates for just for representing points on like the Cartesian plane. So like if you have like this is, I don't know, 2, 1 or 2, 3, why not? If that's 2, 3, we can represent that as a point struct. That's the idea. We can call the variable p, and inside of it, it will have the x part and it will have the y part. It will have the 2 and the 3. That is the beauty of it. We can keep them both together instead of having to say, because before we'd have to make it like two different variables, like double p's x, double p's y, and that gets unwieldy, I think you can imagine. So we can name those things. We can make a variable called p that is of type point. We're making a brand new type for ourselves, and that will hold an x and a y coordinate. Okay, so let me show you this. To make a struct, you say struct, and then the name. We're going to call it point, and this is the new type that you make for yourself. It's called point. And then you put the kind of stuff that goes inside of it. So it looks like this. You have a double x inside of a point. Every point gets an x, that's a double. And every point gets a y, that's a double inside of it. So that's a 2D point, yeah? And you can make different points however you'd like. And the way to make this p now is you say point p equals 2, 3 in braces. It's like array notation. It works and it makes this struct. Okay? And we just made our own type. It's called point. It didn't exist before. It gives us brand new types to use. Okay? So let's code this much at least. So vim structs.cpp. So here's our struct point double x double y. So this defines a new type called point. Every element, every value of type point holds an x and y coordinate inside. That's the beauty of it. And you can make a point by saying point p equals 2, 3. Point q equals 4.5, 7.89. Yeah, that's the beauty of it. Oh, and also, the most important thing that I want to say I intentionally forgot, but I totally forgot, is the semicolon at the end. It's a very, very important thing to remember. It's not like a function definition. It needs a semicolon. It's like a little declaration. And there's a fun little quirk of C++ and the C language, actually. That's the reason that it requires this semicolon. Come to office hours, and I'd be happy to tell you exactly why this semicolon needs to be there. It's a weird requirement, and it's an odd thing that's there. So yes, the semicolon is very, very important. It looks like I remembered it here at least, though. So don't forget that. All right, so now some terminology. So the struct itself is the name of the type. So for our example, it's point. So that's the struct. That's the name of the type. It's called the point struct, and you can make a bunch of different values of point type. Okay, you can make p, you can make q. Those values are called objects. Okay, so when we write point p semicolon, we just declared a point, well, that holds an x and a y that we have no clue about. And that object got made as a local variable. It's called p. Okay? If you did point q, it'll make another one. So an object is an element of the point struct type. Okay? It's the object of any struct's type. So p and q below are objects. That's the metaphor. That's what we say. They're objects. And the x and y that live inside each point, because every point gets one. P gets one, q gets one. What was it? 4.5, 7.89. It also has its own x and its own y. And those x and y's are called fields. Okay? Those are called fields. So that's one way to say it. So p has two double fields, we say, x and y. Every point gets two double fields. P has them, q has them, they're all there. And another word for field is member variable, or just member by itself. Okay, those are two equivalent words for this case. So p has two member variables, we could also say. They're both of double type, and they're called x and y. Okay, that's the beauty of it. And yeah, those are our structs. You can start them out undefined or defined, and maybe let's start out p undefined. We can eventually give it values. That's the idea. And that works with the dot operator. That's how you do it. That's how you give values to each object. So each object, remember, it has its own fields, like p. P's sitting here, it's like, it's got an x, and it's got a y, and q's also sitting here, it's got an x and it's got a y. And these ones are set. These ones are undefined right now. And these are separate. Like, this is not the same x. This is not the same y. That's what I'm trying to say. Okay, there's two separate places. 4 separate places total. So if you want the individual parts of a struct, you want the x or you want the y, you use the dot operator, which you already know how to use, but now you're understanding where it's kind of coming from. It's like you go inside of the thing and access its value. You've used this with a lot of functions, so there's a concept of functions belonging to objects as well, like strings. We'll talk about that soon, don't worry. So yeah, if you want to access a member variable, or a field, those are the same word, you can say the name of the object dot the name of the field that you want to access and get out. Okay? And you can use this to both set and retrieve. So you can say p.x equals 42, and that will set p's x to be 42. Or you could say cout p.y, and that would just get the value and print it out. Okay? So let's see here. How do I want to say this? So p, how about this? p.x equals 42, p.y equals 43. Dun, dun, dun. And then you can see it out. Let's make it all pretty. See out that, and then p.x, and then a comma, and a space, and then a p.y, and then a new line. Yeah, so this will print out p all pretty. Oops. I always do that. There we go. So there's 42 and 43. We got them out. And we also set them. So you can use that same notation for both. And now, that's all well and good. You can use that to initialize, but you can also use that array-like syntax as well. Okay? So this array syntax also sets the point. So you give the values in order. First is the x, then the y. That's important. The order in which these are declared is the order in which the array syntax works. Okay? The member vars are set in the order declared. Okay? And so then we can print out q as well. And say replace with q, replace with q. And so now we have 42, 43, and 4.5, 7.89. So now we have a point p and a point q that hold those different values. Okay? They look like that. So yeah, the dot operator is magical, and that's how you get things out of a struct. Yeah. So let's continue now. Where do I want to go from here? Yeah, this is a nice thing. So remember how I was telling you about references, and that's one way to return multiple values from a function? You can now use structs as well. So that's your second option to return multiple values from a function. You can either use a bunch of reference parameters, like I've shown you, or you can just return a struct which holds a bunch of things automatically, right? So let's make an add function for points. So it'll take 2 points and give back a point with all the pieces added together. So like I don't know, 2, 2 plus 3, 3. If these are points, that should give back, I don't know, 5, 5. That's the idea. So so add the x's and then add the y's together. That's the point. Okay, let's make this add function. So it's going to give back a point, and it'll take 2 points. Point p, or let's call it point, I don't know, 1.2. How about that? And so the idea is it's going to give back an answer, point answer for that, and the answer's x is the sum. It's the sum of 1's x and 2's x. You see that? And the same for y. Okay, and then we just return back the answer. And of course we could have done this in one big line with the array syntax, but I wanted to show this to you this way. So that's all well and good. This works just fine. One nice thing that you would like to do eventually is make these constant references. We love those in this class. So let me show it to you this way right now. Cout, let's see. Honestly, let's make a print point function because I'm getting tired of doing this. So void print point p. What it's going to do is it's going to print out p just like that. And so then we can say print point of our p, and then we can do it for the q as well. Much better. And then we can print point the addition of p and q. Okay, so what this is going to do is it's going to give back a new point and then go off and print it. Or maybe I should just write sum. Point pq sum equals add pq, and then we can give it that. That's probably easier to make sense of. So it's going to add together those two original points, the 42 and the 4.5, to get a new x value, the 43 and the 7.89 to get a new y value. And so that's our pq sum variable now. So it's just a third point. Isn't that quite nice? And then a good idea is always to use constant references whenever possible, because that keeps you from wasting memory and accidentally copying things. Const reference all over the place. And nothing changes. These all work the same because we're not trying to change p, like, oops, p.x++, for example. Can't do that in a const reference. And that's a wonderful thing. So now it works. It does the exact same thing, but it's saving some memory now, which translates to time. No copying for us. So that's the add function on points. How about now we make a negate point function that takes a point by reference, and it negates it, okay? So it's going to negate it in place. Let's say that. And negates it. In place, we say. Let me show you what that means. All right, so the idea for this one is if we have our point P, it exists like this. I don't know, xy is 42, 43, and we say negate point. This is what I want it to do. Because you can also edit things by reference. Negate point, let's see here, negate point P. What it's going to do is it's going to change 42 and 43 to be negative 42, negative 43. Okay, that's the hope. So let's make that happen. And we need a non-constant reference so that we can actually change it. Okay, so negate point p, and then we'll say, then we'll print it again. So let's make this function now. So it's not going to give anything back because it's setting the value. It's changing it. It's taking it by reference. There's no need to give anything back because we're changing the thing that's here. Okay? So we get a point reference, and let's call it something else for fun. Let's call it r. So we're going to take the r, and we're going to negate the x and the y. Okay, so we'll say r.x equals negative, whatever it was. Same for y. Okay, so this will negate the point, and if p was 42, 43, we'll get back, after calling this, negative 42, 43, set to p. And that should print, hopefully, what we think. Yes. So that's negative 42, negative 43. And here's what's happening on the stack when we do this. Because remember that passing by reference is a bit weird, so let me draw that. So we have, down here in main, we had, I need a big main, don't I? We had a bunch of local variables. We had p and q. Let me just draw those. I know we had more. We had p, which was 42 and 43. Then we had q, which was, x was 4.5 and y was 7.89. And then we had pq sum, which also existed, but I'm not going to waste time drawing that. And then we call negate point with p as the argument. Okay, so again, I'm going to use different colors because of the way I want this to work. This is negate point. And everything that belongs to negate point, including its local variables, I'm going to color in green to prove my point of this getting changed. Okay, so the idea is this R was passed by reference. It's going to be set to whatever is passed along. It's saying it's going to be set to P itself. Okay, so really what's happening is it's essentially when we pass P to this function, the parameter R is initialized like, it's like point ampersand R equals, point reference R equals P. That's what's happening in that interfunction dreamland that we know about now. So R is going to be an alias for P itself. It's a new name for the same thing. So down here, I can write R next to P. And if I say r.x, I get this same x as p's x. If I say r.y, I get this same one. We're not copying, we're passing by reference. And that's the beauty of it. So now it's going to go and change rx equals negative rx. Well, that's just p's x, negative 43 as well. So I hope you see what's going on there. And that's why it's going to print it out. It's going to change it, and when it gets printed, it will look different. Okay, so that's why the answer is negative 42, negative 43. And now let us keep continuing because we're ready. We are ready for classes. I'm so excited. So this is one of the highlights of this semester. This is one of the most powerful things I'm going to teach you. Okay? It's called classes. And it builds on top of structs, which is why I teach you them first. So a class is all about data. So that's the part that we inherit from structs. Just like structs. You have your data, you have your objects, but you also have the addition of operations on those objects. And that is where all the power lies. People love classes because they allow for object-oriented programming is the fancy term here. Okay, so let us discuss. So what are some examples of real-life objects that you know about that actually go and do things? Like objects that have operations that work on them. What are those operations? What is their data? Yeah? So think about this. Maybe take a second to write some things down because this is really going to help, I promise. So, for example, let's take my cat. My cat is an entity that exists in the world, and maybe we can make an object of the cat type. Cat Lonzo. Declare. And this is the beauty of it, because the data associated with this cat can be whatever we want. Like, I don't know, maybe Lonzo has like a name and an age. But the beauty of all of this, the beauty of classes, is that you can also have operations, functions that belong to your types. Instead of, well, of course you already have Lonzo.name equals whatever you want. That's my cat's name. And you can do it like this. You can use the struct part of it. But the beautiful, beautiful thing about classes is there are also functions inside of this. There's like, I don't know, have birthday. So, or maybe just the birthday function. Then increments the age whenever my cat has a birthday. Maybe there's a meow function, or like a speak function, for example. And these can be associated with Lonzo. Maybe there's an eat function, which calls the grow function. And these all exist inside of Lonzo, so they get to access his name and his age, and it's all beautiful and very, very powerful. So here's an example of how that might work. It's like Lonzo not dot age equals something, or not seeing out anything. It's like Lonzo dot meow. Parenthesis, parenthesis. You've seen this before in vectors, in strings. this is where it's all coming from. These things are classes, okay? So here's one real life example, and of course you can have dogs. d.woof, for example, is the idea. That's where we're going with this. And then the essence of everything is that you can represent it as a class. There's always some data, there's always some operations that you can associate with anything in existence, right? Like this PowerPoint itself. Let's get meta. Let's be like every PowerPoint. This is lecture 14, for example. You can say every PowerPoint, you can add a new slide, and it can have a name, classes, for example, and you can give it things, and your PowerPoint lecture can hold all its little slides, but also a bunch of functions that potentially take parameters. Yeah? That's the beauty of it. So hopefully you came up with some good examples as well, but these are mine. Okay. So data plus operations. We have some data. We have, I've given you this running example of points. Let's do stuff with points. Okay. So are you ready? Here are some operations we would like to have on points themselves. So in addition to holding data, we want points to respond to our command. So we can say p.negate, p.add with a q, p.scale, make it larger by twice its size. Yeah? That is beautiful. We would like to be able to do this to our points. And the answer is to use classes instead. And here's how you do it. You say class. Instead of struct, you say class instead. And then you say point again. Dun dun dun. Are you ready? Again, you have the semicolon, as usual. You require that. Let's make sure that I am where I think I am. I think so. So you give all this, and then you put the data. That's totally fine. The data can appear wherever you'd like. You still have your double X and your double Y. There is something special that goes here. We'll get into it in a second. And your double Y. And then you have all of the functions that you would like to have inside of your point. You have like negate. And that's a void function, right? And it operates on points themselves. It's wonderful. Void negate. And then, like, I don't know, you can have add, which returns back a new point, right? Point add. And it takes another point, maybe by constant reference. Point O for other. Who knows? Then you can have scale. So you can have scaling a point, and maybe that works on the point itself. So it, just like negate, it changes the point. So that will be a void function. Void scale by some double amount. Some amount C. And these are all beautiful. These are the operations that you can have in addition to the X's and the Y's. You see that? So each, you don't usually write it like this, but if you had a point P that looked like this, X42, Y43, it's like there are extra functions down here. There's like negate that work just for this P. Scale that works just for this P. Okay? Changes its 42 and 43, not somebody else's, just its 42 and 43. And then the last thing that is interesting and useful is public. This is required. It's public and then colon, and we'll talk about this later. Just remember that this is necessary right now. That's what makes all of this stuff visible to the user. It's a weird little quirk that you don't need that in structs, but you need it in classes. So yeah, essentially all you have to do is replace struct with class, and then you can start adding functions in addition to your member variables. Okay, that's enough words. Are you ready? So, let's let's do this. Let's do this right now. We're going to say, and then eventually we're going to do this. Dun, dun, dun. Here are all of my definitions now. So a class, it's very similar to a struct. It defines a type. It builds a new type for you to use, but it also allows you to have operations on that type. Okay, that's the key. And a class is just the name of a type. Okay, just as usual, just like a struct was the name of the type. So point is the class, but P is the object. Okay, an object is a value of some class's type. So it's if we say point, let's go back to blue. Oh no. If we say point P, point is the class, P is the object that's getting made. Yeah, that's the idea. And okay, you can have member variables. Those are the same. Fields and member variables, those exist, and they are the same as their struct equivalents, so I don't have to tell you anything extra there. They exist, and you can use them just the same. But now you have functions that live inside. In addition to member variables, we call them member functions. But the common word, the most common way of saying it is methods. Okay, so from now on, I'm going to try and use the word methods. Methods are the same as member functions. They are the functions that are inside a class. They're the operations that get performed on the objects. And the beauty of this, I've thrown the word object around a lot, is this is the key to a very popular programming style called object-oriented programming. Okay, it's something that I'm required to teach you, and it's very, very popular in industry. So if you're somebody who's not so much about the theory, but a whole lot about the practice, pay attention to this, because this is going to be used for the rest of your life if you go into industry. Okay, it's called OOP for short, but it's object-oriented programming. It's using classes and objects to model the world, to make your cats and your PowerPoints, etc. Okay, so those are my new definitions for you, and now we can go and we can make the point class. Okay, so public is a weird little thing. It is going to allow the user to see what's inside. Okay, gives the user access to what's inside. Okay, and that is that's the idea. So we can make as many points as we want. We can set them as usual, but we can now use these operations. We can say p.negate. And what that's going to do is call the negate method on P itself. It's going to change P's values and not Q's. Okay, so let's see if I can draw this, because this is important. This is what we need, but I've only given you part of the story here. Oops. Go back. Can we select without it changing? Yes, we can. Okay. Okay. Can I group? Yeah. Beautiful. There we go. And so now, instead of these semicolons, you can give the actual definitions. They can live. They can live in here. Those are the answers with braces. And those are what you need. Okay? And the reason we use this kind of concept, the reason the dot exists at all, is because we want this method to act on the P. So if this were P was 1, 2. And we also had a Q that was, I don't know, 3, 4. If we said p.negate, it's like P had its own special negate method inside of it, and it only worked on P. And what it's going to do is it's going to replace P's X and P's Y with the negated forms. That's what p.negate should do. That's what we would like it to do. It's not going to go around and affect Q in any way. That's a separate point. If we wanted that to happen, we'd say q.negate. They're not the same. It's not equal. Okay, that's the idea. It operates on P. Okay, it acts on P, not anything else. It's like P is the first argument to like a different looking function. That's the point. And that was a horrible pun, I'm sorry. So let's see if we can get this implemented. Okay, so I'm going to do all of this. I'm going to show you it working. Are you excited? So I'm going to draw some stuff on this slide. We're going to talk about how negate works soon. We'll either get to that this set of slides or the next set of slides. But that was structs. Let us take a lot of this and go to classes. Okay, so are you ready? Instead of struct point, we say class point. And now we can have member vars, or sorry, member functions / methods, which is a wonderful thing. And you also have to say public. This is necessary so that the user can see what we're doing. Okay? And you also need the semicolon at the end of a class definition. And now I can add my member functions. Hey, are you ready? Are you ready? We have, bam, we have negate, void negate. We have add, and we have scale. Okay, that's it. That's what's going to happen. So let's do this. Let's do this. What negate does, it needs to operate on a certain point. So we'll say, boop, point P, P.x equals 1, P.y equals 2, and we'll also have a point Q sitting around, so that's a little bit different. We'll say Q.x is like 3, and Q.y is 4. So now I have point P and point Q. I want to be able to say P dot negate, and then print out P. So cout P.x space, let's just do P.y. And this should end up being negated. Okay, that's the idea. We would like this to print -1 space -2. Yeah, it's going to operate on P itself and negates it. Okay, that's the idea. So let's make this happen. It's definitely not happy about my little ellipses, so let's fill those in. What does it mean to negate a point? Well, we need to flip the x and y member variables. And that's the key. Okay? When this gets called on us, we have an x and y to work with. It's whatever our current object is. Okay? Oops. It could be P, it could be Q, depending on how we call it. So we say x equals -x, y equals -y. That's negate. And then add is very similar. We know this one already. I can actually just copy it from here. It's got to make a new answer. And the only difference is it needs to use our x and y and o.x / o.y. That's all. So instead of 1, it's just x. It belongs to us. That's our own stuff. And then 2 is o. Okay, that's all. That's the only difference there. And then scale is going to be very similar to negate in that it's going to change x and y by a constant c. So x equals c times x, y equals c times y. Okay, so we scale that. So those are our methods. They're acting on whatever object we give to the dot method. So we say p.negate, it's going to negate p. We say q.negate, it's going to negate q's x and y. That's the beauty of it. So that's negate, that's add, and that is scale. Let's do negate, and we'll print it out. Okay? Boop, boop. This is classes. Are you ready? Are you ready? Oh, it's -1, it's -2. Yes! Let's talk about why this was working now. Okay, so I know this was a lot. It's going to be important to study this, but let's talk about why this at all worked. So let's talk about this method. Okay, so it's going to be weird. It's going to be a little odd, but it's going to make sense, I promise. So here's our main function, and we have p and we have q. So p was 1, 2. That was its x and y. And q was 3 and 4, right? And that was its x and y. And when we called negate, it's a method. It exists inside of every object. So p has a different negate method than q because one works on p, the other works on q. So I'm about to call p's negate method. This is what happens. It secretly gets past p itself. Secretly. That's the beauty of it. That's why it works. So up here to negate, it takes no parameters, but it secretly gets p because it has the x and it has the y. It knows about it. That's its x. It knows about this x. We can say x and get that. We can say y and get that. Okay? They have the same name. If negate uses x now, the x points straight to here. Okay? Inside of p.negate. If you say x, you really get p's x. If you say y, you get p's y, and that's the powerful part. So maybe I should put this in bold. The current object that you're calling this method on, if it's p.negate, it's p. You're calling it on p. The current object's member variables are the ones that are visible inside a method. So if you say p.negate, your x and your y to negate are p's x and p's y. Okay? So you get p's x when you call a method on p, like p.negate, and then use x. Okay? That is, I think, what I wanted to say there. So that's the idea. Let's use these other methods now. Let's make I don't know, sum equals p.add with q. So it's a bit different. You see that? Like, it didn't need 2 parameters because it implicitly got the first one with p dot. So now it's going to add its x and y, its current x and y, to the other point, calling it O, O's x and O's y. Okay? That's quite nice. And so that's the sum. Let's print that one out. We can say, instead of, we can replace it with sum. Oops. There. We'll say sum x and sum y. We'll print that out. So this should make, it should print. Remember that p is now -1, -2, first of all. It should print 3 minus 1, which is 2, and 4 minus 2, which is 2, right? Hey, we did it. You see that? That's wonderful. That is so wonderful. Then we can scale. Let's scale q, because why not? So q.scale by 42. So it's going to multiply everything of q 3 times 42 and 4 times 42. So that's going to be the new x and y. So this should be, I don't know, whatever 42 times 3 is, and whatever 42 times 4 is. Yeah? That's what scaling does. We get 126 and 168. Beautiful, huh? So these are all method calls. We are acting on P. Okay, we're doing something. We're adding, we're negating, we're scaling, and sometimes it updates the values. Like scale, it's going to update q's x and q's y. negate is going to update p's x and p's y, and add doesn't change your current object. It gives back something new. Okay? You can do whatever you'd like here, and you have options. Just don't forget this public. We'll talk about it later, and that is that. So this is our first example of a class. It is data, so this is our data part, and this is the operations on the data, usually. Okay, that's the key, and in between these braces goes a whole lot now. Your data in addition to all of your operations. The world is wonderful. Okay, so that is, I think, all I wanted to say here. So that is my example of classes, my first example of classes for you. We kind of did it a bit lazily, and we're going to fix that next time. We're going to make a nice little library, separate it into different files. We're not going to implement inside of the class like we were doing, because that's all kind of bad style, but it's a great place to start, I think. And so this is where I want to leave you this class. We will come back next week and talk about how to be fancier, how to be proper. But this is good enough for now. So I will see you next week.